In section 3.4, the mole and molar masses, we're going to take a look at how to count atoms and count molecules by weighing, by measuring the masses. And there's a little bit of a topic at the end about working in reverse from percent composition back to empirical formulas, so we'll take a look at that as well. But the primary focus on this section is the mole and the molar mass. And the whole concept here is based on the idea that what we understand is that matter is comprised of atoms, and often those atoms combine to form molecules. And so since matter exists as individual particles, these little molecules, which are too small for us to see, we want to have ways to count them, to figure out how many there are. And so that's what we're going to look at here. And we're going to look at two conversion factors that allow us to count numbers of molecules from mass. So we begin with our discussion of what's called the mole. And one way of thinking about the mole is to think about units of counting. The one that we are most familiar with in everyday life is called the dozen, D-O-Z-E-N. When we measure things in dozens, what we're doing is we're saying, look, there's going to be a lot of these, so let's use a bigger unit. Let's not actually use the real number, let's use the number of dozen. So a dozen eggs or a dozen donuts. There's really not that much of a reason to use a dozen if we're just counting 12, because 12 is not that large of a number, and everybody can deal with the number that large. But what happens if it gets larger? What if you have 144 of something? That's a pretty large number. And so we might have a gross, G-R-O-S-S, is 144. So bigger numbers also have names, but we lost a lot of that terminology in modern society. We don't use it very often, but dozen is still used. So by analogy, the mole is essentially serving the same purpose. We know that if we have a sample of carbon, for example, when you look at your pencil, there's a very good chance that your pencil is made out of a substance called graphite. And graphite is 99% carbon. So it's really a large cluster of carbon atoms. So when we measure out a certain amount of graphite, carbon, there's a certain number of atoms there, and we might want to be able to count those atoms in certain cases. So we use the mole as a method of doing that. Now, some of the methodology that we use, some of the details of this that we use in general chemistry is a little bit outdated. There's a lot of research that goes into figuring out how to define units. So the mole is one which is actually defined a little bit differently now than is discussed in your textbook, but that's perfectly fine. We'll use this slightly outdated definition and go with that. So we're going to define the mole in the following way. We're going to pick an element, and we're going to pick carbon, and the reason we pick carbon is because we were carbon-based life form, so we like carbon. We're going to define it this way. If you have 12 grams exactly of carbon, then you have 1 mole of carbon. That's essentially the definition there. A mole of carbon is exactly 12 grams of carbon. And there are reasons for doing that, and there are reasons why people are moving away from that, but that's fine. Now keep in mind 12 grams is the same as 0.012 kilograms, because a kilogram is 1,000 grams. So we're going to define it that way. A mole is the number of atoms that you would have if you had exactly 12 grams of carbon, but keep in mind with isotopes, not every carbon atom is identical. Some carbon atoms weigh around 12 AMU and others weigh around 13 AMU. So we're going to define it specifically for carbon-12, that if you have exactly 12 grams of carbon-12, you have a mole. Now, one problem with that is that how do you get exactly 12 grams? That's an issue. So that's one of the reasons we move away from those sorts of definitions. So another way of thinking about it is to say this, that 12 grams of carbon, which by the way would be, smaller than a handful. If you took took one of your fingers, and that was made out of pure carbon, it would weigh around 12 grams. So you're thinking of about a fingerful of carbon, this black soot. If you had that amount, 12 grams or 1 mole, there's definitely some number of atoms that are in there. How many? Well, that's a good question. How many is it? People have been trying to figure that out for a long time. And as it says in here, the currently accepted value of that, how many carbon atoms, carbon-12 atoms would be in 1 mole, or 12 grams, is 6.0221418 times 10 to the 23rd atoms. That's a very large number. It's not a number that we could count very easily, so you might ask, well, how do they get that number? And that's a more involved question that we're not going to cover right now. Notice it has a lot of sig figs there, so we're going to round it to 4 sig figs, 6.022 times 10 to the 23rd. And quite frankly, for most calculations, even 6.0 times 10 to the 23rd is sufficient, but we'll go with 6.022 with most of our calculations. So, if we have a mole of carbon-12, we have 12 grams of carbon-12, we have approximately 6.022 times 10 to the 23rd carbon-12 atoms. Okay? And we're going to use that number. We call it Avogadro's number, N sub A, as the mole. That's referring to a certain number of atoms. So if I say I have 1 mole of oxygen molecules, 1 mole of O2, by definition, I have 6.022 times 10 to the 23rd O2 molecules. If I have a mole of nails that you use to nail wood together, I would have 6.022 times 10 to the 23rd nails. So that's our mole. Our mole is defined based on the mass of carbon-12, but we're also going to make the claim that this number, Avogadro's number, is the same thing as a mole. The mole is a counting number, just like a dozen is 12 or a gross is 144. A mole is 6.022 times 10 to the 23rd of something. Now, here's an example of counting and mass, although they're using weight here. This picture here of the hardware store, where they have a bunch of nails and you can take some nails out and go do your building project. Notice there's a scale next to the nails. And the reason for that is we're not going to ask you to count the number of nails when you buy them, because that would be too tedious if you need a lot. And it would also be too tedious for the worker who's got to ring you up at the cash register. So what we're going to do is we're going to weigh them. You're not going to pay by nail, you're going to pay by weight. So in this table here, it says, what happens if you have a box of 3D nails? The D refers to pennies, probably because nails used to be sold by the penny. You'd either pay a penny or 2 pennies or 3 pennies for a certain number of them. So they use that symbol D. So 3D box is just saying a particular type of nail. And the size of it is 1.5 inches. And here's how many nails you would get in a pound. So in the factory, they would actually measure these. They'd make these nails as close to the same size and mass as they could. And what you'd find is that for that particular type of nail, you would get 635 nails in a pound of those nails. So the logic here then is that if you weigh the nails out, you're essentially counting them. A different type of nail, the 60 box. So a box of the 60 nails. Those are a little bit larger, 2 inches long. You get about 236 nails in a particular pound, and then there's a bunch of nails that are shown here. So you can use those as conversion factors, and here's the logic as we get through below the figure. Suppose we have 1,000 of these 4D nails, 4D common nails, a particular type of nail. How much would it weigh? Well, we come back to our chart and we look for 4D common. Be careful, there's 4D casing in that table, but there's also 4D common. What it says here is that in 1 pound, there's 316 of those 4D common nails. So if we have 1,000 nails and 1 pound is 316 nails, we would take our 1,000, that's our given value, our measurement, multiply it by the conversion factor, 1 pound for every 316 nails, and that would tell us that we have 3.16 pounds. What if we went back the other way? What if I said, hey, I'm going to weigh out 5 pounds. How many nails do I have? Well, you weigh out the 5 pounds, and there's 316 nails for every pound. So you multiply it by 316, and that gives you 1,580. 1,580 of those nails. You've now counted those nails. What if you had a different type of nail? The 10D box. That's the third one in the table. Well, there's 94 nails in one of those pounds. So if we have 5 pounds of those nails, and there's 94 nails per pound, that means that 5 pounds gives us 470 of those nails. So notice in the two final calculations, what we're doing is we're counting them by weighing them. 5 pounds of this type of nail gives us 1,580 of those nails. 5 pounds of another nail gives us 470. Why? The 10D box nails weigh more, so you get fewer nails because they're bigger, they weigh more. So the number that you're going to get is different if they weigh differently. And that'll be important for us when we deal with atoms and elements. So now here's a little picture of figure 3.2. That big number, 6.022 times 10 to the 23rd. How much is that? And the answer is it depends on the material, and it depends on the state of the matter. So for example, if you take sulfur, which is that yellow powder, if you had 1 mole, which by the way weighs around 32 grams, 1 mole of pure sulfur would cover that dish there, that little glass watch dish that's right there. It's sort of hard to see how big that dish is, but it's probably around a 4-inch dish. So the diameter of that dish is around 4 inches. Well, what about copper? Copper is more dense, so it takes up less space. Copper is in that smaller dish in the middle. It's that sort of rusty looking color or reddish looking color. Copper it's more dense than sulfur, so 1 mole of that takes up less space. That would be in the middle. Mercury is even more dense than copper, and it's actually a neurotoxin, so for that reason it's put in a glass container, not open to the environment. It also evaporates, by the way. It's a liquid at room temperature, so it does evaporate. Mercury is there on the right. That's a mole. That's 6.02 times 10 to the 23rd atoms of mercury. And then in the balloon, notice how big the balloon is. That's a good-sized balloon compared to those. The helium is a gas, so the state of matter is important there. So gases occupy less volume in general than solids or liquids, so that high helium is taking up a larger space. But that's a mole of helium. That's 6.022 times 10 to the 23rd atoms of helium. That's a mole. So now we get into some of these conversions, and we're going to take a look. There's a little picture here of 3.3, just sort of to make a point, is that hydrogen reacts with oxygen to form water. 2H2 plus O2 forms 2H2O, so that's based on our balanced equation there that we covered in the previous section. Because hydrogen and oxygen are gases, they show a little picture here showing you those reactants in gaseous form by putting them in balloons. So 2 balloons of hydrogen plus 1 balloon of oxygen. Notice it's a 2-to-1 ratio. The volumes of gases combine according to the number of moles of the gases. So because there's 2 H2 reacting with every 1 O2, you need twice as much volume of hydrogen gas. The reaction occurs, and then you form liquid water. Liquid is much more dense than gases. So now they're showing you a picture on the right of the liquid water, which is formed from that reaction. Those gases, boom, they explode and form water, and that water is a liquid, which is now going to occupy a really small volume because it's more dense. Liquids are more dense. And they're going to place that down there in that little graduated cylinder on the right, and they're showing a little blow up of the volume, measuring the volume. So you can measure the volume of the water once it's been produced from that reaction. On the right of that figure, thrown in there, is a way to do conversion factors. If you want to do the conversion of number of moles of something, You multiply by Avogadro's number, and that gives you the number of atoms if it's an element. If it's a compound, you multiply it by Avogadro's number, and that gives you the number of molecules. That's an important little picture there. That picture is showing you how to do probably one of the most important conversion factors we do in chemistry. The reverse is, if you have the number of atoms or molecules and you want to know the number of moles, you divide by n sub a, Avogadro's number, 6.022 times 10 to the 23rd. So that little picture there is shown to prepare you for the examples that are coming up. So sample problem 3.5, let's take a look at that one. Calcium is the most abundant metal in the human body. Interesting. A typical human body contains roughly 30 moles of calcium, which is to some extent our bones, but also our central nervous system has a lot of calcium. Determine A, the number of calcium atoms in 30 moles of calcium, and B, the number of moles of calcium in a sample that contains 1.00 times 10 to the 20 calcium atoms. Okay, let's take part A first. We have 30 moles. Well, what's a mole? A mole is 6.022 times 10 to the 23rd atoms. So if it's calcium, it's calcium. So 1 mole is 6 times 10 to the 23rd. How many would 30 moles? So solution A, 30.00 moles of calcium times Avogadro's number. That's going to give you the number of atoms. So coming back to that little picture on the right of figure 3.3, take a look at what they did. If you have the number of moles of calcium, you multiply by Avogadro's number, and that will give you the number of atoms of carbon. You don't have to memorize Avogadro's number, but it sure does make it easier for you if you do. What about part B? We're going to go the other way now. We have the number of atoms, we would find the number of moles. So that's to the right in this picture in figure 3.3. You divide by Avogadro's number. So in part B, 1.00 times 10 to the 20 calcium atoms, divide by Avogadro's number, and that'll give you the number of moles. Now, I recommend using dimensional analysis, which they do here. In part A to this solution, notice that by multiplying moles of calcium times number of atoms of calcium divided by number of moles of calcium, the moles cancel and you get the number of atoms. That's helping you figure out the correct answer by checking the units. If the units come out to what you expect them to, then there's a good chance you did that calculation right. It's not proof, but it's a good chance. What about part B? In part B, we want to find the moles, number of moles from the number of atoms. Well, you take the number of atoms that's given, multiply that by 1 mole of calcium divided by 6.022 times 10 to the 23rd calcium atoms. The atoms, the number of calcium atoms cancel and you get moles, and that tells you, oh yeah, we were looking for moles, so that's probably right. So notice when you're calculating the number of atoms, it's usually a very large number. When you're calculating the number of moles, it's usually a very small number, or at least smaller than the number of atoms, that's for sure. So try these practice problems. Now, let's get into something called molar mass. With molar mass, it's related to molecular mass, but it is a different quantity. So we're going to start by looking at what is an AMU. Notice I never talked about it on the lecture in section 3.1. What is an AMU? Well, an AMU is a very small mass because it's the mass of an atom, or it's the mass of a molecule. An AMU is 1.661 times 10 to the minus 24 grams. That's a pretty small mass. However, one way of looking at it is to take the reciprocal of 1.661 times 10 to the minus 24 grams. If you take the reciprocal of it, what you get is the number of AMU in 1 gram instead of the number of grams in 1 AMU. So 1 gram is 6.022 times 10 to the 23rd AMU. Well, notice that's Avogadro's number. And so Avogadro's number, despite our discussion earlier, is really just a conversion factor between grams and AMU. That's really all it is. So now, let's take a look at how we use that. This picture here in figure 3.4 is going to show you a lot of information. That looks dense, right? Grams, moles, number of particles, whether that be an atom, a molecule, or a formula unit. A particle is a small object. So an atom is a particle, a molecule is a particle. This is showing you all the conversion factors. So I'm going to go through this little picture here a little bit. This picture you can refer to as you do these problems. You'll get better at it as you practice. Suppose we have the number of grams of a substance, and we want to find the number of moles. Divide by molar mass. Suppose we have the number of moles, and we want to find the number of particles, number of atoms, for example. Okay? Multiply by Avogadro's number. Now, suppose we have the number of particles. Divide by Avogadro's number. That will give us the number of moles up at the top. Suppose we have the number of moles now, and we want to find the number of grams, the mass. Multiply by the molar mass. That's down at the bottom on the left, and that will give you the number of grams. So there's 4 directions that are shown here. And so there's 4 possible steps in these calculations. So now let's go through and take a look at an example. Sample 3.6. Determine the number of moles of carbon in 12 grams of naturally occurring carbon, and B, the mass of 0.905 moles of sodium chloride. Okay, let's take a look at this. Let's do part A first. It says naturally occurring carbon for the following reason. Earlier we talked about carbon-12. That is not naturally occurring carbon. Naturally occurring carbon has carbon-12 and carbon-13 in a mixture. So we're not going to use 12 grams as being 1 mole. We're going to use the value in the periodic table. So notice it doesn't say periodic table in here. That's going to be your strategy. You go to the periodic table. The naturally occurring amounts, the naturally occurring atomic masses are the ones in the periodic table. In periodic table, carbon has a mass of 12.01. It's very close to carbon-12, but not the same. It's either 12.01 or 12.011. So that's the value we'll use. So here's the strategy and the solution. You take the mass, 10 grams, that's given. Notice I'm not saying 10.00 just to save a little bit of time in words. 10 grams of carbon divided by 12.01 grams of carbon will give you the number of moles of carbon, 0.8326. That's coming from this chart. Look for grams. Grams is the mass. If you want to find the number of moles, what do? You divide by the molar mass. The molar mass of carbon is 12.01. Right off the periodic table. Just go off the periodic table. That'll be the molar mass. So 10.00 divided by 12.01 is 0.8326 moles of carbon. Now, in part B, it says, here's the number of moles, find the mass. Going the opposite. So you come back up to this chart. Number of moles is going to get the mass. You're going to multiply by the molar mass. That's over on the left on the bottom. So 0.905 moles of sodium chloride, multiply by the molar mass, and that will give you the mass of sodium chloride, which is 52.9 grams. Where'd that 58.44 come from? Do you remember when you calculated molecular mass early in the chapter? It's the same calculation. Molar mass is calculated by taking the atomic masses of the elements, adding them together for the formula. 1 sodium, 1 chlorine. Sodium is 22.99 grams. Chlorine is 35.45 grams. Those are from the periodic table. You add those two numbers together, you get 58.44. And then you can use that chart to show that. Practice problems, try those. Here's another sample problem. We're going to go to the next step now. We're now going to combine all the 4 calculations, mass, moles, and number of atoms or molecules. Part A. Determine the number of water molecules and the number of hydrogen and oxygen atoms in 3.26 grams of water. Let's just take part A first. Notice what we're given here. We're told 3.26 grams of water. So one of the things you have to get used to in these problem-solving sessions with yourself is the number you start with could be the last word of the sentence. So you've got to look through, you've got to dissect this sentence. There's a lot of information in there. Determine the. That means I'm not telling you what your you've got, I'm telling you what you want to find. Number of water molecules. Okay, so you're going to find the number of water molecules. And, pay attention to that, and means you're going to do another calculation even after that. You're going to find the number of hydrogen atoms, and you're going to find the number of oxygen atoms in 3.26 grams of water. So the number you're going to use to start this calculation off is shown at the end. So let's take a look. We're given that there's 3.26 grams of water, and we know that water is H2O. So how are we going to go about this? This is a lot of information. So I'm going to come back to that chart. If we have the number of grams of substance and we want to find the number of it, we're going to go from the left all the way to the right. And how do we go all to the right? Divide by the molar mass to get the number of moles, and then multiply by Avogadro's number to get the number of particles, right? So top on the left and then bottom on the right. Those are the two steps. That's about as complicated as it gets. So let's take a look here. Solution A. We start with 3.26 grams of water. We divide by the molar mass, 18.02 grams. How did I get 18.02? From the chemical formula. 2 hydrogens, 1 oxygen. Periodic table. Hydrogen is 1.008. Oxygen is 16.00. You add those up. 2 hydrogens plus 1 oxygen, that gives you 18.02. Then we're going to find the number of molecules of water. So we multiply by Avogadro's number, and that will tell us that water, the number of water molecules is 1.09 times 10 to the 23rd. Okay, 2 steps. This is called a chain of calculations, and if you don't want to do it as a chain, you want to do it as 2 separate calculations. You can. Notice the dimensional analysis at work here. Grams divided by grams in the first step leaves you with moles, and then moles divided by moles leaves you with number of molecules. But that's not the answer. They did not ask us for the number of water molecules. They asked us for the number of hydrogen. Actually, I take that back. They did ask for the number of water molecules, but they also asked for the number of hydrogen and oxygen atoms. So in one water molecule, there are 2 hydrogens. So just multiply it by 2, right? If you have 50 water molecules, how many hydrogens? Well, there's 2 hydrogens for every water, so 50 times 2 would be 100. So that's what they did here. They multiplied it by 2 to get the number of hydrogen atoms, which is twice the number of water molecules. But what about the number of oxygen atoms? There's only 1 oxygen atom for every 1 water molecule, so you're going to multiply it by 1. And obviously multiplying by 1 is the identity function, or the identity operation. So you're going to get the same number of oxygen atoms as you have water molecules. Part B is reversing it. Part B is saying, look, now it's carbon dioxide, CO2. We're going to give you the number of molecules. What is the mass? So we come back up here. Number of particles, number of molecules on the right. If you want to find the mass, you divide by Avogadro's number to get the number of moles, and then you multiply by the molar mass at the bottom to get the number of grams, the mass. Okay, so take a look at solution B. They give you the number of molecules. You divide by Avogadro's number to get the number of moles, and then you multiply by the molar mass to get the number of grams. Answer in scientific notation. Okay, so that's the solution to that one. Practice problem A, practice problem B, practice problem C, try those. Finally, there's a lot in this section. By the way, this section right here is perhaps the most life-saving section for your future in Chem 1100 and 1200. If you can do these problems easily, the ones I just went over, that is going to help you so much in Chem 11. If you cannot do problem 3.6 or 3.7 or the practice problems that come with them, seek out help, because those 2 problems are the ones that you need to do a lot of separate calculations in Chem 1100 and Chem 1200. It's essential. And there is no sentence in here at the beginning that says, hey, in this section, you better be able to do these calculations. If you can't, it's going to kill you in the next course. But I'm going to tell you right now, in section 3.4, these calculations are essential calculations for what is to come in your future. Okay? They're not hard, but you are probably, if you're taking this course, probably never seen them before, or if you did see them, you only saw them a little bit. You really want to master these problems, and if you need help with them, let me know. Now, at the end is something, a type of problem, empirical formula from percent composition, that is just sort of thrown in here at the end. It is not discussed in its full context, and the reason for that is they're setting you up for the next section. In film, producing film or literature, there's a term called foreshadowing, where you show something in the story that's going to come back as being a big thing. And so that's what's going on here. They're showing you a little simple little calculation that you're going to use in the next section. So let me go over it a little bit here. Empirical formula from percent composition. Remember, the empirical formula is the simplest formula that shows the ratio of atoms of each element in the compound. So for example, NaCl, there's 1 sodium for every chlorine. HO, there's one hydrogen for every oxygen. Hydrogen peroxide has a formula, H2O2. There's 2 and 2 of each element, but the empirical formula is just HO, because the lowest ratio is that they're the same 1 to 1. So in this problem, they say, here's your percent composition by mass. We learned how to do that calculation in the previous section. 30.45% nitrogen, 69.55% oxygen by mass. Find the empirical formula. How do we get back to the formula? It's the reverse of what we did. So here's the way we go about this. This is one method. It is sort of the tried and true method of general chemistry throughout the country. What you do when you have this problem is you assume you have 100 grams of the compound. And keep in mind, we're trying to find a formula. The formula is going to be, we know it has nitrogen, we know it has oxygen. It's going to be NO or NO2 or NO3, or it's going to be N2O, or it's going to be N3O. It's not going to be N70O54. It's going to be small numbers, 1, 2, 3 as the subscripts, maybe 4 at the most, but most likely 1 or 2. Small ratios. Now, here's how you go about it. You assume you have 100 grams, and the reason we pick 100 grams is that since those percentages add up to 100, notice they do, add those two numbers together, and you'll see they add up to 100. The masses can add up to 100. And then that way, the ratios work out as being the same as the masses. So assume you have 100 grams. If you have 100 grams of the compound, then you would have 30.45 grams of nitrogen. And you would have 69.55 grams of oxygen, right? If you have 100 grams, adding up the percentages has got to be equal to adding up the masses. They're both going to be 100. So we assume we have 100 grams. That way we've got the numbers we've already are given can be used as the masses of the elements. Now, there's 2 steps here. One is you use the atomic masses of each element to find the number of moles of each element. So that's the first step. So look at the solution. 30.45 grams of nitrogen divided by 14.01 grams of nitrogen. Where'd that come from? It came from 2 places. One is the 14.01 came from the periodic table for nitrogen. Look it up, you'll see it there. The 16.00 came from the atomic mass of oxygen. That's from the periodic table. That came from there. Now, why are they dividing by that atomic mass? Come back to here. If you have the number of grams on the left and you want to find the number of moles, you divide by the molar mass. That's what they're doing here. You take that percentage, assume it's grams, divide by the molar mass of nitrogen, that gives you the moles of nitrogen. You take the mass of oxygen, you divide by 16.00 grams per mole, that gives you the moles of oxygen. The key step is find the moles of each. Once you've done that, we know the ratio is going to be 1 to 2 or 1 to 1 or 1 to 3, small ratios. Take a look at the moles. If you look at those 2 numbers, roughly estimating, it looks like there's half as much nitrogen and twice as much oxygen. 4.347 looks to be twice 2.173. Now, how do you make sure? You divide each of those numbers by the smaller of the two. So the smaller of the two is 2.173. So if you divide each of them by 2.173, you get 1 for the nitrogen, and you get something that's really, really close to 2 for the oxygen. And that gives you the ratio. 1 nitrogen for every 2 oxygens. So you divide by the smaller of the two. If there's 3 elements, you divide by the smallest of the 3 for all of them. So it looks like it's a 1 and a 2, so the empirical formula would be NO2, right? When you get 1 and a 2, those become the subscripts. But remember, in chemistry, we don't write a 1 as a subscript, we just write the symbol for the element. So NO2 means 1 nitrogen, 2 oxygens. That ratio 1 to 2 came from these moles. So the step here, the procedure is take your percentages, assume they're grams, divide each element by the molar mass from the periodic table. That gives you the moles of each. And then divide those moles by the smallest, and that'll give you the ratio. Then you've got your empirical number, your empirical formula. The answer would be NO2 because it asked us for the empirical formula. The answer would not be 1, 2, or 1, comma 2. It would be NO2. Okay, so try the practice problems on those. Try the checkpoints. Those are good ones. Those problems will set you up for the next section, which is combustion. And combustion is pretty involved, so you got to be able to do these first. So try those problems, sample problem 3.8, and then the practice and checkpoints. But again, really go through all of these questions in this section. There is no warning. Really, if I were writing this book, I would have a little warning label on this section about how important these calculations are. Okay?